Block design. First of all, if you can do a basic comparative randomized experiment, you can do a block design. It's just kind of doing it with repetitions simultaneously, like doing the same experiment twice on two different sets of individuals. Yeah, that's kind of how it works. This is used when you have different types, male and female. So let's imagine that you want to do an experiment and it's to check out a new kind of medication to address some kind of condition. And you look at your sampling frame and you think, wow, I've got men and women. There may be a gender effect with this medicine. So a block randomized experimental design will be the way to go, because if you have males and females mixed up, you're going to add extra variation into your results, which you don't want. If you separate them and do the experiment on each of the two genders separately, then you get an extra margin of control. All right. One thing you don't want to do, you might note that explanation sounds a lot like stratifying in a survey, stratified random sample. There you look at, naturally occurring characteristics or categories within your sampling frame, and you just want to make sure everybody's included. So you take random samples proportionately for all the groups within your larger sampling frame and put them together in a sample. Blocking is different, all right? So stratifying is used in a survey. S goes with S, as it often does. And blocking is used in experiments, so don't get them mixed up. So definition of a block: this is a group of experimental units or subjects, like all men or all women, that are similar in ways that are expected to affect the response to treatments. So in a block design, the random assignment of units to treatments is carried out separately within each block. This is important. Now, you're not going to really understand the true meaning of this until you see the flow diagram. But once you do, you're going to see that some people might put the randomization in the wrong spot. All right, so we'll get to that. So blocking comes before random assignment into groups. All right, so you split up into men and women, then you randomize each of those two categories into groups for treatments. That's before, blocking comes before that. So when you see it, a block design is like doing multiple experiments at the same time. So here is the scenario, and it's out of your book. It's on page 317. And it looks pretty complicated, but it's really not. Let me just go ahead and read this off for you. So some researchers are interested in how fertilizer will affect the quality of fruit that comes from tomato plants. So initially they wanted to use 18 tomato plants of the same variety for the experiment, but the garden store that they went to get them only had 12. So they're short 6. So they said, okay, we'll check out the nursery down the street. So they went there and bought 6 more plants of that variety. So now they've got 18, but they have a concern that the tomato plants from the 2 different stores are different somehow, or have received different care. So how can we design the experiment so that differences between the stores don't mess up our attempts to see differences among fertilizer levels? We can't measure the effect of a store the same way we can the fertilizer, because we can't assign it at random. In other words, you can't tell a tomato what store to come from. Okay? So, because stores may vary in the care they give plants or in the sources of their seeds, the plants from either store are likely to be more like each other than they are to be like the plants from the other store. So when groups of experimental units are similar like that, it's often a good idea to gather them together into blocks. By blocking, we isolate the variability attribute to the differences between the blocks so that we can see the differences caused by treatments more clearly. All right? So it's a way to input some extra control. Now looking at the diagram here, you can pretty much see that the top, just the top part here, is a basic, completely randomized experiment. And then it's repeated down here. So you start out with your 12 tomato plants from store A and the 6 from store B, and you separate them. So all of the store A forms block A, and all the plants from store B form block B. Now from there, you randomly assign into groups, and the groups get treatments and so on, right? So you'll notice that there's no random assignment here, and there's no random assignment here. So you can't just pick a tomato plant and say, oh, you're from store A, without really knowing if it's from store A or store B. Just the way you can't assign women randomly into the women group. There are women, right? You just can't take a person and say, oh, you're a woman, or take anyone. Like you randomly pick a guy and say, well, you're destined for the women group, so change genders. See what I'm saying? So that initial blocking split does not take anything random. This is block A for store A. Anything from store A goes in it. This is block B for store B. Anything from store B goes in there. From there, you put random assignment, and then they form groups, and each group gets a treatment, and then you compare how well the fruit performs, okay? Okay, so when I ask you how many groups there are, well, you know what? There are going to be 6 unique groups. Group 1, Group 2, Group 3, and Group 4 is still going to get treatment 1, but it's from a different store. So these 3 are not going to be renumbered 1 through 3 because they come from different stores, right? But now if I ask you how many treatments there are, you might glance at it and say, oh, well, there's 3 here, that's 6. No, because this treatment control is the same as this treatment control. It's just no fertilizer. This treatment of half dose is the same as this. Same with the full dose and the full dose. So you're just using the same 3 treatments, but you're repeating it twice. All right? So be careful when you have to count up the treatments. At the end, you compare, how the fruit is, whether it tastes good or whatever. And you do that within the blocks, but really technically not between the blocks. You've already taken out the variation for the stores, so why put that back in? So be careful of the random assignment. Be careful of the number of treatments. Be careful of the number of groups. Now there is one thing here that I'm uncomfortable with. And if you really stop and think about it, you might figure it out. Because remember our 3 principles of statistical design of experiments? One was randomization. Well, we have that. See, random assignment. And then control. Well, I think the control here is pretty good, right? They're basically 18 tomato plants of the same variety. And you've added the extra control for the blocking. And you've kept them all under similar conditions. So your control is good. But what about your replication? All right, you've only done the experiment once, and I agree that's a problem, but look within it. Do you have sufficient number of units in each group? And I would tell you that 2 is a little on the light side, maybe a lot. Even 4 is a little on the light side. So when these folks write up their experiment, what they need to do is list that as a limitation and say, look, we tried to get more plants, but we just couldn't find any. So that's what's happening. You're running the same experiment twice at the same time. It's easy. Just remember all the little details. All right, so be careful when reading the diagram. You only have 3 treatment groups, not 6. And remember, the goal is to ensure that each treatment group will have 4 store A tomatoes and 2 store B tomatoes, right? So back here, 4 store A, 2 store B. You have it for all 3 treatments. That way you can isolate the effect of the fertilizer and eliminate any differences between store A and store B because they're now in each treatment, okay? All right, so the advantages, you can control your confounding. That helps to control confounding, which could be the origin of the store for the plants, right? So blocking reduces the variation among the treatment groups. That's a good thing. Okay, so blocks do control, I guess I just said that. They control the effects of some outside variables by bringing those variables into the experiment to form the blocks. You have more precision because you can draw separate conclusions from each block. This is so important that there are some books that consider blocking a fourth principle of statistical design of experiments. Now, I don't think your author does, right? He only does the first three. So if you're asked for three, list those. Control, randomization, and replication. You can get by on those. But blocking is so important that when you look at your sampling frame, you might consider, can I block or should I block? You know, if you have some kind of obvious categorical variable there that you think, ugh, that could confound things, you know, gender effects, racial effects, whatever, then go ahead and block. Just find those extra experimental units, because the disadvantage is that, well, if you're doing 2 experiments from what normally would have been 1, you have to divide up your sample sizes, right? So if you do that, you're going to end up with maybe mighty small sample sizes. So consider when you design the thing to get more subjects. So that is blocking. Hopefully I got it across well. If not, watch it again. There's always the book. You can read up on what the author says. The author's pretty good. Not too many people read him, but he makes a lot of sense. All right, so an AP tip. If you're asked to do any kind of describing of your block or why you're doing it, just say you're reducing variability within treatment groups, because that's what blocking does. It's not a discussion of comparing differences in the blocked groups. All right, this is the last of our topics, okay? And this is matched pair design. You see this quite a lot. This is where you have, you're comparing only 2 treatments. For example, if you have a taste test, or you know, the Pepsi challenge years ago, they used to always have competitions to see who preferred Pepsi over Coke. They were rigged. Pepsi always won. All right, there are 2 ways to do this. One way is an absolute stinker, all right? Let's just say you're one of the people that is going to take a treatment. What they would want to do would be to match you up with somebody similar to you. Now, maybe you can see the flaw in this, because even if you have an identical twin, that may not be enough for a good similarity. So, yeah, if they just grab a person off the street and say, okay, you're a girl, she's a girl, you're 5'6", this person's 5'6", you know, whatever, you know, there's always going to be a lot of variability between the 2 of you, and that's a problem. So in order to address that, why not just leave you to get both treatments? Because what better control could there be for you than yourself, right? Because there is no variability. You are you. So if you're going to, well, let's just look at the next thing. Order of the treatment matters and should be randomized. So imagine this Coke and Pepsi challenge thing. You go up to a counter, they toss a coin, it turns into a head, they know which one to give you. Let's pretend it's Pepsi. You take a swallow, you think, oh, that's okay. And then maybe they give you a cracker or something to cleanse your palate, because that's a problem. And then they give you Coke, and you just rate them. Which one's better, all right? And then the next person comes up. So that's matched pairs. Now, the cereal leaf example is on the next slide. I don't want to really read it to you, but it's not in your book. It is here, already posted. So let me try to paraphrase. So researchers are going after cereal leaf beetles, and they want to know if they're attracted to colors, specifically yellow or green. All right, they know that there are these pests in the field, and what they do to find them or to get them is to mount sticky boards in the field. And if they can pick a good color to attract them, so much the better, all right? But they're just not sure which color would be best, green or yellow. So they're going to design an experiments to compare. Now the second paragraph is them explaining how they would do this with a completely randomized design. And it's kind of neat. They would just go ahead out into the fields where the oats are growing, and they would install poles. Every so often there would be poles. And then they would randomly pick a pole to get a color. And they would pick half of them randomly and put green on them, and the other half would be yellow. So there you go. Then they would trap the insects and see which of the two attracted the most for color. Well, the issue that they run into here is that if the poles are actually located too close to the boundary of the oat field, they are bounded by alfalfa. And alfalfa is a natural food source for these cereal leaf beetles. So if you stick a board on there, I mean, you're just going to get more insects because there's going to be more insects there. So if there are a bunch of yellow ones there, then yellow may seem like a better color than green, when in fact it's just the effect of the alfalfa. So a better option would be to put the poles out there and stick both colors on them, right? So no matter if you've got a ton of insects that are kind of right there, or if you don't have too many, you still have both colors available for them to pick. And so you would cancel out the effect of just where the insects naturally occur in greater frequencies. See what I'm saying? Now, the randomization would come because when you put these things on poles, there's got to be one above the other. And that may influence, the little critters. They may like the lower ones, they may like the upper ones. So what you want to do then is flip a coin to figure out where they go, like which color goes on top and which color goes on the bottom. So if you flip a coin in its head, let's just say that makes the yellow go on the top. All right? So you see, the poles are the individuals, and the two boards that are on it, the two different colors, are effectively the treatments. Okay? So that's how matched pairs works. Between the Coke Pepsi thing and the cereal leaf, hopefully you're good to go with it. There may be other examples in your book if you need to read them.